In this video, I'm going to discuss laminar and turbulent flow in a pipe. We're going to look at some of the physics of laminar and turbulent flow, talk a little bit about the transition between laminar and turbulent flow, and talk about an oil line experiment which can be used to measure the pressure drop in laminar and turbulent flows, as well as to see some of the features of laminar and turbulent flow. First, let's consider our pipe, and let's remember our important non-dimensional number, the Reynolds number. If you recall back, the Reynolds number can be given either as the density times the average velocity times the diameter, a length scale, and for pipe flow that will be the diameter of the pipe, over the dynamic viscosity. And of course the kinematic viscosity is just the dynamic viscosity over rho, so we can also write it this way using the kinematic viscosity. Physically, this is a measure of the viscous force to the inertia force. And when the Reynolds number is small, the viscous forces will be dominating over the inertia forces, and the flow will be stable and laminar. And we've seen what the laminar flow solution looks like for this parabolic velocity. We'll see it again in a moment. But that is because the viscous forces are dominating. As the Reynolds number gets higher at a certain point, the inertia forces start to dominate, and we start to get some interesting accelerations, velocity fluctuations, which are on the acceleration side of the Navier-Stokes equations, the mass times acceleration side, and the flow transitions to turbulence. So we have a flow which has already developed, and when it's fully developed, we saw in the previous video that for laminar flow we get a parabolic velocity profile. So if I were to draw my velocity versus y, I would see my nice parabolic velocity profile, which we've shown all the equations for. Also, if I were to put a point in the flow, and I look, what is the velocity at this point right here as a function of time? So now I'll plot that velocity as a function of time. That velocity is going to be a constant value. It's not changing with time. And so we know everything we need to know about this flow. It occurs at the lower end of the Reynolds numbers. The velocities are constant. They're not changing, at least for a fully developed laminar pipe flow. The velocities are not changing with time. And we have our nice parabolic velocity profile. Okay, so as the Reynolds number increases, we will have transition to turbulence. As the inertia forces get higher, the accelerations in the flow start to do some interesting things. We're still going to have a fully developed flow, but now it will have a turbulent velocity profile, and I'm going to sketch that roughly as something that is a lot flatter than the parabolic profile. And again, I'm going to look at what happens when we put a point in the flow, and we look at the velocity as a function of time. So the velocity as a function of time once we have a turbulent flow. Once we have that turbulent flow, the velocity as a function of time will no longer be constant. What we're going to see is that we have a signal that is noisy. And being noisy, we can take an average value of this. So this is U bar, the time average velocity, and of course these deviations from the average are these fluctuating velocities. So once we get a turbulent flow, the velocity will not be constant in time, and when we draw a velocity profile like I have sketched on the pipe above, we're going to draw the time average velocity profile. So here I have a radial coordinate r, and I'm going to plot U bar, and what I'm going to see is that I get a velocity profile that's much, much closer to uniform with very sharp gradients going down to 0 at the wall. This is the time average velocity profile. If I looked at an instantaneous, it wouldn't look as smooth as this should look if I drew it very nicely. But what do we notice here? In comparison to the laminar velocity profile, the gradient at the wall is much steeper. And the fact that it's much steeper means that we have higher shear stresses in there in comparison to a laminar flow at the same Reynolds number. And I'll talk more about the same Reynolds number having a laminar and a turbulent flow in a moment. And so we expect in the fully developed flow, the pressure forces are being balanced by the viscous forces because the inertia going in and out is the same. The velocity profile is the same in and out. And so if the shear stresses are higher, of course, we must have a higher pressure drop than in comparison to a laminar flow. And why does it come about that we have this? Remember our conservation of mass equation, du dx plus dv dy plus dw dz is equal to 0. That was our conservation of mass equation. And if we have this fluctuating velocity component in the u component, it must be balanced in order to conserve mass. If this is changing in time, we must have corresponding changes in time in the v and w components of momentum in order to always conserve mass, because these terms always have to add up to 0 or we're not conserving mass. And so the fact that there's a fluctuation in the u component of the velocity means there has to be corresponding fluctuations in the v and w. And that tells us a couple of truths about turbulent flow. One, it cannot be steady. There is a time dependence, which we can average away and look at the time average. But there is an unsteady component to it, and it is three-dimensional. You cannot have a velocity fluctuation in just one component. It will be in the 3 dimensions. The time average velocity can be one-dimensional, but the actual velocity signal will be a 3-dimensional velocity signal. So we know that actual turbulent flow is 3-dimensional. It's changing with time. And when we take the time average, we see that there are higher shear stresses, and so we expect higher pressure drops in turbulent flow. The reason that the profile is flat like this is, imagine that you had the laminar profile, and we had a high amount of momentum here in the center where we had the maximum velocity, which was twice the average velocity. In the turbulent profile, if we have a velocity fluctuation in the u component, it means we have a velocity fluctuation in the v component, and that v component is going to carry some of this momentum, this high momentum fluid, towards the wall, in the y direction or in the r direction, and carry some of that high momentum here. It's mixing the flow. So all of these velocity fluctuations are doing a great job of mixing the momentum in the flow, and if we mix momentum, we end up with a much closer to a flat profile where the average velocity is much, much closer to the maximum value. And this also carries through if we have temperature gradients in the flow, or if we have concentration gradients in, they will be much better mixed in a turbulent flow than they are in a laminar flow as well. So I hope that gives a little feel of the physics of the turbulent flow. Then we're going to look at how to use these. One of the first things to notice is the entrance length. If we had a developing flow, of course, maybe we start with a uniform velocity profile out here. And remember, we had our boundary layers that eventually merged, and we got our fully developed region and our developing flow or entrance region. In a laminar flow, we can look at this entrance length. So this region here, I will call the entrance length LE. And LE is approximately 6%. LE, non-dimensionalized by the diameter d, is approximately 6% of the Reynolds number. So we can always estimate how much of our pipe was subject to these higher pressure drops in the developing flow region by using an equation like this. About 6% of the Reynolds number times the pipe diameter will give us that length. Turbulent flow, because of that velocity fluctuations and that mixing, develops much, much more quickly. And an expression we can use for the entrance length in a turbulent flow is approximately, again, normalized by the pipe diameter, 4.4 times the Reynolds number raised to the 1/6 power. What do those things mean? Well, first we have to talk about when we transition from laminar to turbulent flow. And I'm going to revisit this in a moment. But the accepted engineering value is that somewhere around a Reynolds number of 2300, we have a transition from laminar to turbulent flow. So the Reynolds number based on the diameter of the pipe, if it's below 2300, we can have a stable laminar flow. And if it's above 2300, we can have turbulence in the flow. And in a real application, we probably will have turbulence. That means that if I use the value of 2300 for the Reynolds number in this expression for the entrance length in a laminar flow, I see that the maximum laminar entrance length is 138 pipe diameters. That's a reasonable length, but if you remember back to the introductory video, you see that these pipe runs can be extremely long, running the whole length of buildings, the whole length of rooms, and 138 perhaps could be insignificant compared to the entire length of the pipe. But in almost all industrial flows or domestic flows, the flow will be turbulent in the pipes. And if the flow is turbulent, we can ask what is the turbulent entrance length at that same Reynolds number, 2300. If the flow transition to turbulent there, then it's only 16 pipe diameters. And even if we go up to a very high Reynolds number, if we go up to a Reynolds number of 10 million, using that expression, the entrance length is still only 65 pipe diameters. So now looking back at the videos of those real pipes, you can imagine that if we only account for fully developed flow, we'll have a very good approximation of the pressure drop in the entire pipe. The entrance length will be a fairly insignificant addition compared to these long pipe runs, 65 pipe diameters even at a very high Reynolds number. Okay, I want to talk about something called the oil line experiment. It's related to the way that the data that we used to calculate pipe flows was originally determined, and it's also something that we often do in an undergraduate course. And what we do in the oil line experiment is we have a reservoir of oil, and we pump that oil nicely into a pipe, and we have, so here we have oil, here we have a pump, we pump that into our pipe, and then maybe we put a nice window on here so we can see what's happening as the oil comes out, and then collect it into another pipe and return it back to the reservoir so we can keep circulating this through here. And then what we're going to do is we're going to put pressure taps along here, and we're going to measure P1, P2, P3, P4. And in so doing that, we can see how long it takes to develop, because if the pressure difference is linear, we have the fully developed solution. If it's larger than linear, if the pressure drop between pressure taps is decreasing, we see that the flow is still developing. And there's one more feature that we put in this. We put a small pin in here so that we can disturb the flow, and we can pull this pin in or out in order to make contact with the flow or not. And we do that in order to trigger turbulence when we want to have turbulence. We'll talk about that as we talk about the laminar flow. So if we're looking at this oil line and we have reached a fully developed laminar flow, and we look at the oil coming out of this pipe, you can probably find videos of this online if you search for them. But if you look at the oil coming out of here, what you're going to see is that we have a main jet of oil that comes out and shoots a ways out the pipe before falling to the bottom and being collected and returned again in the pipe, returned in the bottom pipe to the reservoir. But what we also see is that there's a secondary stream that falls more quickly. So this is the main flow, and then there's another stream that falls here, and it's connected by a web between here, so a very thin film of oil between those two. And we can see what's happening here by thinking about that laminar velocity profile. We had a nice parabolic velocity profile where the center line velocity was 2 times the average velocity, so we have a lot of momentum in the center of the pipe. We have a large region with very low momentum on the outside of this pipe. When we get to the end of the pipe, that low momentum fluid has almost no inertia, and so it falls very quickly. All the low momentum fluid from the outside of this wraps around the outside of this and falls much more quickly, whereas this high momentum core fights gravity for longer and gets shot out further. And you see the connection as that low momentum fluid fell down and fell more quickly. The other feature you would notice if you saw this is that the oil is fairly translucent, it's nice and clear, it looks like it's a smooth flow. When we transition to turbulence, however, we see a very different thing. We see that we no longer see the two pieces. We see a flow that comes down. It's not as translucent anymore. It's a little bit more cloudy because of all the mixing that we have in the pipe. And we also see that it falls a little bit faster than the laminar flow. It falls a little bit faster than the laminar flow, and all of these differences can be explained by these velocity profiles. We have a lower momentum here. The maximum velocity is lower, and so it falls more quickly under the influence of gravity. And we have much more momentum close to the wall, so there's very little fluid that has low momentum next to the walls, and therefore you don't see that separation of the low momentum fluid falling off there. Now the neat thing with the oil line experiment is that if you're on a nice concrete pad in a quiet place, then you can increase the Reynolds number to very high numbers. In fact, you can easily achieve laminar flow at a Reynolds number of 8,000 or maybe even 10,000. But what it means to say that the transition to turbulence at a Reynolds number of 2300 occurs is that once you exceed 2300, the flow is unstable. And if a disturbance is there, it will become amplified and become turbulent. So if we carefully increase the Reynolds number to 7,000 and we see the nice laminar profile, and then we insert that pin into the flow upstream, we'll immediately go to the turbulent flow solution, and we can see it very clearly in the oil line experiment. The very interesting thing is, recall that I said that a turbulent flow has a higher pressure drop. Well, what's happening in this system? In this system, we're setting the speed on a pump to drive a flow rate of oil through this system. If the flow is turbulent, the pressure drop if the flow is laminar, the pressure drop is lower than it would be if it's turbulent. So let's say we manage to keep a laminar flow up to a Reynolds number of 3,000. We get a flow rate that corresponds to that solution that we've shown for that pressure difference across that pipe, and it's the laminar solution. We have a given pressure drop. Now we put the pin in, and the flow transitions to turbulence, and therefore we get a jet coming out of it that looks like this. We can see that it's a turbulent solution. It's more jagged on the edges. All of those features have changed. But now the resistance is higher. The pump is seeing a higher resistance because the pressure drop is higher, because the shear stress is greater on the walls, and therefore the flow rate starts to decrease. And as the flow rate decreases, the Reynolds number goes down, and when it gets below 2300, it will relaminarize, and you'll see the laminar flow solution again. And then the resistance will go down, and the flow rate will start to increase, and you can get a situation where it's going back and forth between a laminar and a turbulent solution. And so you can have laminar and turbulent flow at exactly the same Reynolds numbers, and you often have these transitional flows where it's spending some time in the turbulent regime and some time in the laminar regime, and very often this has to do with the fact that the resistance is changing, and therefore the flow rate is slightly changing, and we're going back and forth between laminar and turbulent flows. And we'll see this when we come to see how we do our calculations, that there is this region of overlap where we could have laminar or turbulent flow, and it's of course not a place where you often want to be working. And the safest assumption as an engineer is that there will be enough disturbances, there will be a disturbance to be amplified, and the flow will be turbulent. So we will very often say transition occurs at a Reynolds number of 2300. In subsequent videos, we're going to look at how to do calculations to calculate the pressure drop.